Okay, all set?
Yeah, we're good.
Great. It's my pleasure to introduce the Zebracorns. They have brought ROS to the first competition, which many of you I'm sure are familiar, but is one of the biggest high school robotics competitions in the world. So,
Thank you. So thank you all for having us. Good morning. My name is Marshall Massengill, and while professionally I work for VMware, I'm also a longtime mentor for the Zebracorns, which is a FIRST robotics team based in Durham, North Carolina. It's my distinct honor to introduce these 4 amazing students who have all served as leaders for our programming sub-team, 2 of which graduated this past year and were instrumental in helping us embrace ROS and make this transition happen, and 2 of whom are still in high school and are continuing in their predecessors' footsteps. So allow me to introduce you all to Niall Mullane and Olivia Fujikawa, both current students at the North Carolina School of Science and Mathematics, which is our home base in Durham. And allow me to introduce you to Anya Shepard from UT Dallas and Ryan Greenblatt, who's attending Brown University. And I also want to introduce you to my fellow mentors, Kevin Jaggett from NVIDIA and Meg Massengill, who has recently become my better half and is in the audience documenting our presentation for us. So thank you all, and without further delay, here's Niall.
So as Marshall mentioned, we are a high school robotics team, and we are in Durham, North Carolina, in the United States. We were founded at the North Carolina School of Science and Mathematics in 2002, and since our founding, we opened up our membership to members of the community, so not just students from our school. As far as FIRST robotics teams go, we are out of the norm. We strive not just to win competitions, but to push for what is possible within robotics. And at the same time, making public our discoveries to elevate the competition as well as ourselves. As a team, we're fairly software heavy, and we're here today because this past year, we implemented ROS on our robot, becoming the first team in our robotics league to do this. We hope to continue this to become the first team in our robotics league to develop a fully autonomous robot. So a little bit more about our robotics league. As Marshall mentioned, we take part in an organization called FIRST, which stands for Inspiration and Recognition of Science and Technology. FIRST has multiple different levels of competitions for different age groups. We take part in FIRST Robotics Competition, or FRC, which is the high school competition. FRC is an international competition with over 3,600 different teams in 27 different countries, and it has engaged over 90,000 different students.
So here are our robots from the past few years. You may notice that they all have very different designs, and that's because every single year the game is different, though there are some common aspects to the game, such as picking up game objects and placing them, or shooting game objects. So the way that matches work is that 2 alliances of 3 teams play each other. The majority of the match is a user-controlled period, but there's a short autonomous period. However, during this user-controlled period, it's possible to automate some actions to greatly improve efficiency, and that's sort of our path to full automation. If we can push forward how much of the match is us performing those automated actions, eventually, well, we don't need a driver anymore.
FRC robots are around 150 pounds and less than 3 by 3 at the base. One of the stricter limitations in FRC is a maximum part cost, so that limits the sensors and the processors we can use. As for software, all FRC teams are required to control direct writes to hardware with a processor called the ros-i. This is so that FRC can override commands sent to the robot on the field. All FRC teams program in C++, Java, or LabVIEW. We program in C++. And FRC teams are required to use libraries called WPILib, which controls interfacing with the field network and hardware. This is because certain WPILib commands, like those to enable and disable the robot, are required by FRC. So we had to incorporate them into our robot code when we transitioned to ROS.
Other FRC teams run perfectly fine without ROS, so you may be asking why we decided to make this hefty transition. A few years ago, we incorporated a coprocessor onto our robot, which was an NVIDIA Jetson TK1 at the time. We realized that ROS makes communication between these processors much more seamless, and that was a really critical benefit to using ROS that we saw. Also, we really like to use the latest and greatest sensors and technology, so iterating through new sensors constantly is something we like to do, and ROS makes that a lot easier. You can get up and running very quickly because of all of the open source code that's already out there. And finally, the way that FRC competitions are set up with 2-minute matches and then 10 to 15 minutes in between those matches, ROS bagging our data during the matches is really important for our success. So if something goes wrong, we can quickly identify the problem and fix it during those 10-15 minutes and be ready again for the next match. Our journey to running full stack ROS began back in 2012 when we implemented stereoscopic vision onto our robot. We realized that the RoboRio, which is the required processor by FIRST, was not good enough, so we implemented a NVIDIA Jetson TK1 as a coprocessor. From there, we implemented a neural network to identify game pieces on the field, and one of our teammates went to a summer program at MIT and discovered ROS when the students there used ROS to control autonomous vehicles and brought it back to the team. That next year, we had ROS and Labby working together, and this past year, we fully transitioned over to C++ and ran full stack ROS.
So since I flew all the way here, the students decided that I should present one slide anyway. I get to talk to you guys about the RoboRio hardware and how we ported ROS to it. So as the students mentioned, the RoboRio, any robot code that touches hardware, the RoboRio is required to run it. This presented us a couple of problems with porting to ROS. The first one, as you can see from the specs up here, it's not the beefiest CPU in the world, so we had some performance issues. As the students mentioned, we use a coprocessor to fix that problem. The bigger issue in the context of this talk is that ROS doesn't exist for the RoboRio, so we had to port it over there. What we did was we took the cross compiler that we used to build normal robot code and used that to build ROS also. The first step for this was getting dependencies installed. A lot of these were available from NI as packages for the NI Linux system. For the ones that weren't, we built them from source. We typically try to target them as static libraries. This just reduced the number of libraries we had to copy back and forth to get things running on the Rio. After that, we were able to build the ROS packages that we needed. Again, like I said, we used the FRC compiler, which is just a GCC ARM cross compiler. Luckily, they provided us with a toolchain file, so we were just able to plug that in and build the ROS packages. Like I said, we tried to build just the packages we needed to keep the install size down, but even so, that was about 150, 160 packages or so. On the Rio itself, we used Python pip to install some of the basic ROS packages, things like catkin, rosdep, and so on. We did have to modify the ROS OS detection to recognize NI Linux. In our case, we were able to just have it be identified as a version of Ubuntu, and that worked reasonably well. This final bullet point here, whenever a robot connects to the field for competition, it reports what it's running, what kind of motors it's using. We modified our version of this code to report that we were running ROS. We were happy to see that over the summer, WPI actually accepted a pull request from us to make this recognition official. So now every time we connect to the field in a competition, they know that we're running ROS.
So as we've mentioned before, that all of the code that directly interacts with hardware, and especially the motors, must come directly from the RoboRio. And consequentially, a lot of our sensor data is connected directly to the RoboRio as well. However, we're able to connect some of our sensors, such as the stereoscopic camera or a LiDAR, up to our NVIDIA Jetson TX2, which we now run as a coprocessor along the RoboRio. So as we implemented ROS this past year, we decided to use Dave Coleman's ROS control boilerplate along with the hardware interface to create an effective read, update, write loop for our ROS control, where the hardware interface, which runs on the RoboRio, interacts with the hardware, reading the sensor data, making that data available to our controllers, and the controllers read that data and also communicate with the high overhead nodes running on the Jetson TX2 that are running the object detection, and we're currently working on the field localization. These controllers take in that data, update the state of the robot, and then write back to the hardware interface, which will directly control the hardware that we're running, such as the pneumatics, the motors, or the digital I/O, or whatever we happen to have on the robot for that year. Something that this setup also allows us to use is a simulation interface, which we'll talk about more in a couple slides.
A key part of how we've been able to achieve the things we've been able to achieve with such a limited processor is by offloading a lot of the work to our motor controllers. So we used embedded CAN-connected motor controllers from Crossroads Electronics, specifically the Talon SRX. And these motor controllers have the capacity to run onboard control loops such as PID with feed forward at 1 kilohertz and simple trapezoidal motion profiling. And they can take input from encoders and limit switches, so there's no need to send data back and forth other than receiving feedback and sending set points. They also have support for measuring current and then doing stuff like current limiting and setting a ramp rate.
We wrote 3 custom controller packages for the CTRE Talon SRX. So the first one was a Talon interface, and this extended the default ROS state and command objects. So the Talon state object included data we got from the motor controller, like current data, encoder data, and limit switch data. The Talon command object included not just writes to the Talons, but also CTRE configuration settings. The Talon state controller published its state data from the hardware interface so that other nodes and other controllers could read that data. And then we made a package called for Talon controllers. It kept one base Talon command controller, which included CTRE native commands, and then child classes for different modes the Talon could run in. So, as Ryan mentioned, PID, motion profiling, etc. These Talon controllers were designed to be able to replace the default ROS controllers in any given mechanism controller.
We used mechanism controllers to unite several different motor controllers as well as other sensor input and driver control. So we had 2 controllers, a drive-based controller and an elevator and superstructure controller. The picture you see is a module for the drivetrain we use, which is called Swerve Drive. It's fully holonomic because each wheel can be steered as well as rotated, which allows for, of course, high maneuverability. We implemented a custom motion profiling algorithm, which used arbitrarily constrained trapezoidal motion profiling to limit the velocity and acceleration at each wheel. For the elevator and superstructure controller, it was super key to limit the motion of the arm and the intake in the elevator to avoid collisions. And using simulation through ROS was very critical for this because it's difficult to test these things without a robot if you don't have some sort of simulation apparatus. And testing things with a robot that involve collision is typically a poor idea. It also helped us with automating things such as coordinating the intake and the arm to quickly obtain game objects and not have to have the driver fully control that type of motion.
So as we touched on earlier, we are running a simulation interface to run our robot code without any hardware on our laptops. We do this by replacing the hardware interface with a simulation interface to act almost exactly the same way, except it will simulate the sensor data and will not talk to any actual hardware. This allows us to run all the controllers that we just mentioned without any modifications to them off of the robot, and that helps us test our code off of the robot. But a lot of the actions of our robot actually rely on FRC-specific match information that we get from the field network, and also the FRC driver station, which will only run on Windows. So we created an RQT plugin to replicate the FRC driver station with all the same features to allow full simulation of all of our robot code. And so as Ryan mentioned, we use this a lot for testing our automated handoff between our intake and our arm. And so what you see there is a fully automated action. And the trickiest part of getting that to work was pathing the arm, grabbing the cube. And that we created we created different RViz visualizations for that to verify in simulation that the arm wouldn't try to go through different parts of our robot and breaking it. So the use of simulation this year greatly improved our robot control, and this handoff may have not been possible without it.
Our team has a couple of main goals for the next few years. First, we're really passionate about bringing ROS to mainstream FRC. First, we've already released 2 white papers for the past 2 years explaining how our methodology and our reasoning for transitioning to ROS. We release all of our code open source at the end of the season for any teams to learn from. And we're hoping to contribute more FRC-specific edits back to ROS, like support for smart motor controllers. We think it's important for more teams to use ROS because it'll raise the overall level of competition, which is beneficial for everyone. We're also hoping to improve our SLAM, so we use sensors like the radar, the LiDAR, and the Z stereoscopic camera to localize ourselves against game pieces and field elements. We want to improve our simulation. So for the past 2 years, we've had a full-scale VR simulation of gameplay using Unreal Engine 4 with a CAD model of our robot. So we want to incorporate our ROS code into that simulation so we can get a more detailed and accurate simulation. We also want to broaden our simulation so that whenever we introduce a new mechanism controller, it's easier to simulate it. Finally, a goal of our teams has been to deploy FRC's first fully autonomous robot. We're actually getting closer and closer to that goal since we're currently developing for a fully autonomous robot at our next competition.
So thank you guys so much for your attention. We were really excited to come out and talk to you. If you're interested in what we were saying, please get involved with FIRST. There are over 3,000 teams around the world, so there's probably one near you as well. If you're specifically interested in us, come talk to us, contact us, take a look at our code on GitHub, or if you're part of a university or company, if you have programs, sponsorships, scholarships, come talk to us. We really want to get involved more with the ROS community and get ROS more involved with FIRST. So thank you again to our sponsors, especially to the NCSSM Foundation, NVIDIA, and Crossroad Electronics. And we have NVIDIA swag, so come talk to us later if you want some. And thank you very much.
Thank you. This is awesome to see. Does anyone have questions?
I think it's amazing that you folks want to build an autonomous robot when it's not required at all. And I think, so you said there's 15 seconds out of the 2 minutes that is required autonomous. So that's awesome, but how do you think that FIRST in general, the competitions can maybe be adapted to encourage more teams to work towards this level of autonomy?
It would probably help if they were better about planning around vision targets and planning around maybe expanding the autonomous period or the points available so that there's less of a gap to bridge. But I would just like to say autonomous cars aren't required. So it's not necessarily because something's required that you have to automate it.
Anyone else?
So I'll make a pitch real quick. The best way to raise the level of play and to encourage other teams to do this is to get more of you involved in this program because these teams desperately need mentors who understand this software. We are a really kind of odd duck in the world of FRC in that most of the mentors on this team understand software and the hardware is largely driven on our team by student development, which is awesome. However, that's not the case for most FRC teams. Most FRC teams are the other way around. They don't have mentors who understand the software. They need people to get involved and get knee-deep into this with these students and become passionate about it, same way we are, so that we can have ROS for the rest of FRC and we can have other teams doing the awesome stuff that we're doing, because we think it's great, and hopefully you guys do too, but we want them to think it's great too, so.
Yeah, okay. Thanks. Just a very nice presentation. I kept being surprised by the level of sophistication of all the stuff that you're doing. I was just wondering, how is the sort of the response or the reaction, if you will, from other teams? It sort of connects to what the last comment was. I mean, all these other teams typically use like LabVIEW stuff, and how do they see you guys? And they're like, no, we're never going to win from you. I mean.
To set the record straight, we're not encouraging every single FIRST team to adopt ROS. There were lots of bumps in the road, and it's not for every team to do. FIRST has a lot of great resources for first-year teams to get set up. And the only reason we were able to do this was because we had a history of trying new things and just going for it. So we don't encourage ROS for everyone, but we do think that we have seen increased interest in ROS. One of our team members worked with one of the you worked with CTRE, right? Yeah, he worked with the Talon developers, and they saw an increased interest in using ROS over the summer as people called in after we published our white paper. So more high-level and experienced teams should really look into ROS as an option, as far as we see it.
Okay, thanks. Very nice work.
What type of control algorithms did you have on the GPU?
So we were working on doing SLAM and localization using LiDAR and a stereoscopic camera. We also had object detection running for vision targets, and we're also using that for object detection of the game pieces. We didn't have as much time as we would have liked to incorporate all of these things into a cohesive product, but hopefully now that we've sort of laid the groundwork, it should be easier to integrate these things going forward.